Now, there are 4 types of lattice defects. Okay. Now, until now we were talking about perfect lattice structure, but in reality when we look at say materials and systems, we see there are a lot of defects in these lattice structure. For example, if you have a FCC center, there may not be one of the atom at one of the face is probably missing from there. So, it is a point defect. So, there are different types of defects also present in the real materials. So, what are those defects? If it can be categorized into 4 types based on the simple dimension. One is point defect, where the defects are at individual points. Then another one is line defect, where the defects are along a line. It could be in different direction, but they are following some kind of one dimensional pattern. And then you have a surface defect, which is like a plane having some defects. So, it is a 2 dimensional. And then you have volume defect, which is 3 dimensional. So, the entire space in 3D space is having some defect. So, we will have individual discussion on each one of these in the remaining time. So, point defects by definition it happens in a crystal lattice where an atom is missing or an extra atom is present, or an atom of different size is replaced, or an atom of different size is replacing an existing atom. Okay. So, either completely missing or completely replaced or a new atom is present. So, these are all happening at a particular point within the material system or lattice structure. So, we call it point defect. Now, what about the line defect? These are imperfections in a crystal structure or lattice in which a line of atoms. So, this is the point, a line of atoms become mismatched with their surroundings. So, there is some non-uniformity in the way the atoms are arranged, but this non-uniformity is in shape of one dimensional, you can say one dimensional in nature or one line. It is not necessary that this line is straight line throughout the material, but when you look at a small range of distance, you can say it is in one dimension. Then another one which is surface defect, it is basically looking at the area. So, that means you are talking about now one more dimension, 2 dimensional defects or areas of defect concentration in the interfacial zone between the crystals. So, this is essentially to do with the grains etc. Anyway, when 2 crystals come close to each other, there could be some defect in that region where they kind of come close to each other, and so grain boundaries we call that. So, if you have a crystal like this and another crystal, so in wherever they come in contact, that is a region where you have a defect. So, it is a plane defect. It is not a point, it is not a line, but there is one more dimension, that is a plane defect. Now, the next one, which is volume defect, it is 3D region, that means 3 dimensional. So, entire volume you are looking at, point, and then 1 dimension, that is line, and then 2 dimension, that is surface defect, and now 3 dimensions, that is volume defect. Examples are voids. Let us say you have an air void inside the material, or you have an impurity which is like a globular shape or some kind of nodules which are present, or even in another shape, inclusions. Okay, it could be needle shape, flaky material. So, we'll show you all that in the coming slides. So, here I just wanted to mention these 4 defects in brief. Now, let us look at some of examples of these defects and how they actually influence the material properties. Let us say in case of point defect, you have interstitial and substitutional. These are the 2 examples of point defects and how they really influence the material property. Example is solid solution strengthening, or even when we talk about alloys. Okay. So, the alloys are essentially working based on this kind of point defects. And then you have swelling of clays, that also is a example of point defect. I will show you in a more clear things later on these 2. And then you have a line defect, okay, which mainly examples are dislocations. There are two types of dislocations, I will cover that later, and how they influence the ductility and work hardening, okay, or strain hardening. The ductility of the material or the strain hardening nature of the material are all influenced by the line defects, or the presence of line defects can actually influence the such properties of the metals. Now, point defects in crystals, solid solutions or alloys. So, you can see the picture on the bottom where these two types of defects are shown. So, one type as I already mentioned, interstitial, where small atoms fit into the space between the larger atoms. So, you can see on the first picture on the left side where you have a solvent metal, it is not liquid, we are not talking about liquid here, we are talking about metals, and then you have a solute element atom. So, the blue one, the small blue one, this one is solute, and the large green one is the solvent. Now, so these are called solid solution, okay. Solid solution, I told it is not liquid phase, it is the metal phase itself, but you have these different types of atoms mixed or in the form of a solution. So, we call it solid solution. Now, the one on the left side is interstitial type, the one on the right side is substitution type. So, what is the difference between these two diagrams? You can very clearly see that the size of the solute is also same size as that of the solvent, green, or similar. I am not going to say same, but it is similar in nature, and more importantly they are actually, the blue one is actually replacing a green one. It is not going and occupying in the space in between like in the first case, but in the substitution case it is substituting or replacing an existing green atom, you can see, or the solvent metal you can see here, okay. So, this kind of explains what what is the difference between interstitial and substitution types solid solutions, and this is heavily used for making alloys, okay. Now, I already told that it might change the properties of the material. So, here we talked about solid solution strengthening. So, strengthening means there is something to do with the strength, it is changing that, right. So, for example, when we mix carbon with iron, that is when we get steel. So, if you use only iron, it does not have much high strength. So, you are actually putting carbon as an impurity, very small quantity of carbon as compared to the volume of or the concentration of iron, but when we mix it, we get steel which is of very high strength, and also other properties will get changed. So, this is the main advantage, or any alloy for that matter, all the alloys are having different type of materials or elements mixed together in the solid state itself. So, look at three region on this drawing here. Region 1 is here, I am going to call it R1, and then region 2 is here, I am going to call it R2, and then region 3 it is R3. Okay. So, now focus very closely on this. In region 1, you can see that there is one smaller atom present at the center over there. Okay. So, when I have a smaller atom there, what will happen to the bond? You look at the length of the lines or the black lines, they indicate kind of the bond, right, bond between two atoms. Now, when I put this smaller atom there, what will happen is the length of this bond, this, all these get stretched, okay, these get stretched. So, when they get stretched, this region will experience a tensile stress. This region will experience a tensile stress. Now, another one is the second case here, where you can see a larger atom is placed at the center or both these R1 and R2, they are substitutional type defect, and the larger atom is placed. So, when you place a larger atom, what will happen to the bond in the vicinity, that the length of the, so when I put this larger atom there, it is going to push all other things, push out the other things, right. So, this is what is going to happen. Now, when this happens, these bonds get compressed, okay, this, all these get compressed as compared to the a little bit far away points or bonds. So, the material will experience a bit of compression. So, this technology is somewhere used for pre-stressing. Even in the glass, the toughened glass which we have, they put some impurities so that the material, there is some kind of compression is generated at the very near surface. So, you get pre-stressing effects. Okay. Anyway, so this gives you a little bit of compressive stress in the region. Now, R3, where you have interstitial kind of defect, you can see here, they are making some changes, but there is not really much of compression or tension which is generated, but they can make a difference in the overall volume, or other type of properties can get affected, okay, or density will get affected, because this space, the air void in between are now filled with some other material. So, all that is different thing, but these kind of alloying or addition of impurities into the lattice structure will have significant influence on the various material properties. Now, I am going to explain about this substitutional type defect. So, for civil engineering, if you really look at, so the previous one we talked alloying, so metal properties will change. Here, we are talking about the substitution. I thought of bringing this example of soil. We use soil for road construction, right. So, and we know that the soil will expand and shrink. So, this is one good example to demonstrate the this substitution, what happens and how it influences the material properties. So, clay, if you go to a paddy field, you will see that during summer it really clay really expands, and you will not see any of these cracks. Sorry, in summer you will see the cracks. When the rainy season comes, this same clay will absorb the water and expand, and so closing all the cracks. So, in the same paddy field, when you go to the paddy field during rainy season, you will not see any cracks, but during the summer all that water evaporates, the soil starts shrinking and then leading to cracking in the map pattern, no regular pattern. So, effect of this on structures, you can say that this on the road on the right side, you can see this kind of cracking forming, you see these cracks, all these cracks. So, that is because the soil below is expanding and pushing out the asphalt material which you see on the surface. So, there is some kind of expansion happening. So, if you are talking here, see this region, there may be some water logging, somehow water will get below the road surface, it will get absorbed by the soil below the road surface, and then once it has enough water, it expands and the tremendous pressure is applied onto the road, and you have the flexible pavement, it just cracks. Now, same thing you can see here, wavy nature, that is also because of the expansion. So, these kind of things you might have experienced, when you ride on road, next time you see whether there are bumpy roads or not. So, it might be something to do with the soil below the road. So, you can think about it, it will be interesting to observe all this. I always say, as a civil engineer, you should keep your eyes open, because most of the things which we talk in class, you will be able to see and feel and experience that, and then try to avoid such failures. Now, buildings also can have this problem because of soil expansion. So, for example, here in this particular building, I mean there are different types of reasons for these cracks. Could be settlement. When I say some region is settling, this is also possible that some other region is expanding and then pushing up the foundation. So, you can see here this sketch here, it shows kind of the soil below. If it expands, it will push, and the beams might get cracked, the foundation might get affected, and that might also lead to cracking of the walls, because overall the structure is getting affected. So, this used to, I mean it is problem in many parts of the world where the soil is of expansive in nature, expansive soil. If it is there, then you have to really think about how to control that expansion by mixing the soil with something, or prevent the soil from getting soaked with water. There are different ways of controlling it. So, but we need to be aware of this. Now, what is really happening when we are talking about defects, etc.? I know this is, we are not talking about metals, but this I thought is a good example to show you and to demonstrate how the this substitutional substitution can change change the way in which the material behaves. Okay. So, here this is a typical clay structure. So, there are, I am showing three types of clays: kaolin and illite and bentonite, the three major types of clays which are used. And what is clay? It has silica tetrahedrite. Okay. So, you can look at this one, the single unit, and then alumina octahedra, which is this unit, and then that is also arranged in a planar structure. So, in the drawing below you have this trapezoid which is shown is silica. All that is written as S in the sketch below, and that is S here, and then you have alumina layer which is the rectangle, darker color rectangle, that is alumina layer. Now, in kaolin clay you have this additional charge, but when water is coming in contact, let us look at the example of bentonite. When water comes in contact, what will happen is, so you have this S layer, that is silica layer, alumina layer, and then silica layer, and here you have another silica, alumina and silica layer. Now, when water is coming in, it goes in between the space. Okay, it goes in between the space between two SAS structure, and that will lead to increase in the volume. Okay, that will lead to increase in the volume. So, if essentially you get larger volume, and this is probably something which we have to avoid, especially when we talk about soil below a particular structure. Okay. So, so your idea is the soil should be treated or prepared in such a way, or the material selection should be in such a way that this kind of water absorption does not happen. Okay. Now, line defects in crystals or metallic crystals. So, what are these line defects? These are imperfections in a crystal lattice where a line of atoms. So, we are now talking about one more dimension. Line of atoms become mismatched with their surroundings. They are also called or dislocations, one type of line defect. And type of dislocation, there are two types: edge dislocation and screw dislocation. Okay. This is showing what is the difference between these two types of dislocations. So, let us say you take a piece of paper, or sorry, a solid material, and then you try to shear it, like I am showing with my finger. You try to shear it. If it is, so I am moving my palm like this, and the force is the direction of motion and the direction of the force which I am applying, they are parallel. Okay, they are both happening like this. But if I do like this a little bit, okay, or in the same direction if I apply, but because of the some kind of internal rearrangement, the direction of motion is like this, and whereas my force applied is they are not parallel to each other. In the first case, you can see this pink, this diagram here, I mean arrow, that indicates the movement of the dislocation or the direction of the motion, and this is the shear stress which is applied. So, that indicates the edge dislocation, whereas in the second case you have the shear force which is applied there or shear stress, but the direction of motion is like this. It is kind of something like this rotation, not like this. Okay. So, that is what is screw dislocation. You can see that there is a it is something like this. Okay. If it is not clear. So, direction of motion is not parallel to the direction of the force which is applied. So, these are the two major the difference between the edge and the screw dislocation. Now, in case of line defect, we will talk about first line edge dislocation, and then we talk about the screw dislocation. So, in the line defects, it is formed by the addition of an extra partial plane of atoms in the lattice. So, you can see an extra partial plane, that is this. Okay. This is the extra partial plane. So, you can count the number of planes in the top two rows. I can say 1, 2, 3, 4, 5, 6 and 7, whereas below the slip plane. So, this is the slip plane, okay, this is the slip plane. Okay. Below that you have only 6, 1, 2, 3, 4, 5 and 6. Okay. So, one extra above the slip plane, one less below the slip plane. Now, that is a sketch right there. At the bottom left you can see an actual image of crystallographic plane showing dislocation in aluminum at a magnification of several million. This is actual image using a microscope. So, you can see that there is this extra layer present there. So, this is a clear this is clearly showing what is this edge dislocation. Now, what is its impact? So, as you see on the top half or above the slip plane, if I say this is the slip plane, okay, yeah, if I say this is the slip plane, above that the gray region will have some kind of compression and this region will have some kind of tension, because in the top half or above the slip plane you have more atoms to be occupied in the same space. So, there is a congestion there. So, that means there will be a compression force in that area, and whereas at the bottom or below the slip plane you will have no either tension or no major effect. Okay. So, essentially there is a stress variation above or below the slip planes. Now, when you talk about deformation, plastic deformation or yield, like I showed earlier the when you shear like this, okay, what is happening is there is a movement along the slip plane. This is the slip plane, the dash line in the horizontal dash line, and now you notice the movement of this blue on the top leftmost region and the blue atom and the red bond here. Okay. That is moving the blue atom or it is not that the blue atom is moving, but the bond is changing, we are shearing the material. So, here you can see that this blue atom in the first case was the first plane on the top, and now that is moving to the second plane, and then now it is to the third plane, and then fourth plane, and then now fifth plane. So, the material has slipped by about one position. Okay. So, you can see that it is kind of very similar to a shear behavior, like similar to what I showed here, you can see here. Okay. So, that is what it is. Now, the force also here you can see the force is towards left on the top and towards right on the left on the left and towards right. So, it is like this shearing action. Now, is some micrographs showing what it really looks like when we look it through a microscope. So, you can see here these smooth lines, these are all indicating the line defects and edge dislocation, and why I zoomed in this red square region, you can see a little bit of horizontal lines also, I mean perpendicular to that. So, I am going to remove this. Yeah, now you can see very clearly that there it is not just the line, but there are also in the other directions. So, all these black lines, black curves, it indicates the edge dislocation along the plane of the image, okay. And where you have the zigzag lines like this, that is indicating that there are also dislocations in the other directions, okay. Just to give you an idea about what it really looks like in the real sense. Now, one on the right side is showing like dislocations around the carbide particles. So, these are the carbide particles, okay, these are the carbide particles. So, you can see that there is some kind of square loop forming around that. So, just to give you a feel of all these edge dislocations. Now, there is another type of dislocation which is called screw dislocation. This is also line defect. So, in the form of a spiral ramp of atoms. So, as you think about a screw, as you rotate the screw moves in the direction like this, whereas your rotation is happening in the direction like this, right. So, same way happens here also. So, you can see on the top right there is this animation of that blue arrow, you can see. It will just start now. Yeah, you can see it now. So, the blue animation, it is going like a screw about the axis, right. So, that kind of indicates how the movement is. So, here on the bottom left, it is to demonstrate how the movement is. Again, in another way, you have stress and stress here. So, it is something like this, okay. So, you can see the progress in the first image, just 1 or 1.5 unit cell, you can see that is where it gets sheared, and the second one you have more than that region gets sheared, the black shaded region, and eventually you have more region getting sheared. But only thing which is, see, if you look at the third image, in the line defect also you will say that it is very similar looking. Yes, but the point is the movement is happening in one direction and this shearing or the defect is in the opposite, not opposite but perpendicular direction, okay. Whereas in case of edge dislocation, both are happening in the same direction. So, you can see here this is what I am talking, this region, that is the region which is getting sheared here, whereas in the case of edge dislocation, this is the region. So, again to recap, this in case of edge dislocation, the force and the direction of motion are in the same direction, are same, whereas in case of screw dislocation, the force and the direction of motion are perpendicular to each other, okay. This also there are cases, and in reality most time this is what you will see, there are cases of mixed dislocation. So, when you take a material system, you might see both edge and screw dislocation. So, here you can see at this point B written here you have edge dislocation, and over here you have screw dislocation. So, you can see this portion is getting teared here and this portion gets slipping. So, this is notation for edge dislocation, like indicating the perpendicular sign, and then this is the rotation angle. Okay. And to summarize, in today's lecture we talked about how metals or the solidification process of the metals. from molten stage to the solid stage, and then how the grain structures are formed, and what is the difference between what the possibility of difference between the grain structure at the near surface and inside. And then we will talk about different type of lattice structure and some key parameters defining them, and then talked about point defects and line defects. So, we will end the lecture today here, and we will cover the remaining type of defects in the coming lecture. Thank you.